Hey, John here. Arg, there be sprites in them thar controller. When is Talk Like a Pirate Day? All right, so today we're looking at the programmer's guide. That's the one that has the cover that looks like this, okay? And here's the section on sprites, section number 9. Okay, so I'm assuming you already know how to configure the VDP and download the initialization code and set up the registers. I talked about that before. In graphics mode number 1, we can also use sprites. So what I'm doing is I'm adding to my last example the m1t1.asm file here, all right? So I've made sprites.asm out of it. I just pushed this all up to GitHub, so it should be there when you see this video on the YouTubes, okay? What are we doing here? Sprites. Okay, so down here, you may recall, I've got this big old config table down here that we use to download the initialization data into the VRAM on the VDP, all right? Now, before, I did not have anything to say about the sprite patterns. Now we do, all right? Big picture first. We have sprite patterns. In addition to the regular old tile patterns, this time the tile patterns, I made little arrowheads that point up and down and left and right and up on, 45-degree angles into, if this was a coordinate grid, the first quadrant would be up here and the second would be over here and so on, right? So I've got some stuff down here that has to do with the actual sprite. I'm only going to put one sprite on the screen, and I'm calling it paddle 0 because I'm working towards an implementation, hopefully, of breakout, where you got a paddle that goes back and forth on the screen, left to right, and this is the position information, and we'll see about that in a minute. And that's the only thing that we need to do to our already existing VRAM code. All right, we're using the same configs that we had before. And all I did is I added some extra, well, we sent this data before. It was just all set to the defaults, which was, these were all set to D0, and we'll see what that's all about in a minute. And up here, I just simply left them all set to like F0 or something like that. So I added these 3 lines, and the position information down below. We'll look in a little bit more detail after we take a look at the manual. Now, if you don't know what a sprite is, and if you're, I don't know, under the age of 30, you may not, because these kind of came and went in the early 80s, and they existed for a very specific purpose. The hardware wasn't smart enough or fast enough to be able to draw and update and move things around quickly on the screen. So you had very special hardware that allowed us to put a single picture like this little rectangle right there on the screen and then move it around, okay? I move it to the left, I move it down, and so on. This image of this red thing and where it is on my captured screen here is controlled with special hardware. I can have up to 32 of these on here at a time. It has other limitations. I can only have 4 on any horizontal row at any one time. And if this is coincident with another one, they have this idea of a priority. In other words, the higher priority ones will appear to be in front of the lower priority ones. All sprites appear in front of the tiled background on the display, okay? And they'll talk about that a little bit in this section right here, okay? So, for example, it says here we have 32 sprites, and they are numbered 0 to 31, and 0 is the highest priority, or outermost, frontmost in-your-face sprite that'll go in front of the other ones, and so on, all right? And it says that they come in 2 sizes. They got 8x8s, and they got 16x16s, okay? The one you're looking at in here is a 16x16. This is 16 pixels wide. It's also 16 high, but I only put, a couple of rows of pixels in here, and the rest of them are, shall we say, blank. And as you'll see, they end up becoming transparent. So that what you have in a sprite is you got like the idea of a foreground color, and the background is see-through. Okay? So, for example, we'll see what this thing is in a minute. all these little arrowheads on the background. As you can see, this sprite, when it moves around, it is not covering up the background above it and below it, even though the sprite is, basically the physical size. If I move it to the left here, you can see it's as wide as 2 of these tile columns, and technically it's as tall as 2 as well, but the top part of here and a little bit of the bottom is transparent, okay? So that's the general gist here. Now it says they come in 2 sizes. They got an 8x8 and a 16x16. Down here it also says that you can magnify them and double its normal size. So an 8x8 will become a 16x16, and a 16x16 would become a 32. Now, magnifying an 8x8 and creating a 16x16 out of it is not the same thing as having a 16x16 to begin with, okay? Because when you magnify a sprite, what we're really doing is double the number of pixels in the horizontal, double them in the vertical, and it paints the same total number of, shall we call them, spots, but each spot in what would be, for example, an 8x8 becomes 4 of the pixels in order to magnify it to a 16x16. So the resolution, we say, is cut in half because each one of the pixels in the sprite is mapped when it's shown as a 2x2, okay? So in this case, what I have here is actually, as we'll see, an 8x8 sprite, but I have magnification turned on, okay? And that makes it easier to see because an 8x8 really is pretty small, right? If I'm going to play around and I want to paddle, you can have tiny sprites if you want, or you can have make it a little bit bigger so it's easier to see. Plus, you can create a big sprite to begin with and then magnify that, and then it would end up being twice the size of the one you see on the screen right now. So that one you see on this screen right now is 16 wide. It's technically also 16 high, but when I set which pixels were supposed to be on, in red, orange in this case, the rest of them are transparent, so you can see through it. Even if it had a hole in the middle, you could see through it and see what's underneath, okay? Now, this paragraph goes on to talk about how you define the sprite and what it's going to look like the same way you define an 8x8 pixel in a pattern table, just like you do in the text and the other graphic tiles we talked about before. And so what we're going to find is a separate pattern table. There's one for the tiles, or what they call simply just the pattern table, right? And then there's another whole table that is the sprite pattern table. And in my file, here's the sprite pattern table. And I padded out to the bottom because I didn't want to type all that in. And here's the regular pattern table, right? I would have preferred it for them to call this like the tile table, and then this the sprite table, or the sprite patterns and the tile pattern. Yeah, whatever. I got into that last time. So they go then on to explain a size 0 is an 8x8, and what is a size 1 sprite is a 16x16. And you'll see there's a bit when we configure how a sprite is defined. It'll be a 0 or a 1, depending on how big it's supposed to be. Now, there's a completely separate bit that is on or off that controls this magnification that I was talking about before, okay? Here they emphasize the fact that there's 2 separate tables. One of them is the sprite pattern, and the other one is the pattern table. Here they go on to talk about while there are 32, you can only have 4 on any one horizontal line at any given time. It says if the rule is violated, the 4 highest priority sprites will be displayed, but the 5th and whatever lower priority sprites might occur on that line at the same time, or behind it, or whatever, will simply not be drawn at all, or as they say, they'll automatically become transparent. That's what that 5th sprite flag thing is for in the status register, to let you know that that is happening. Now, this is kind of a big deal back in the day as well, since we're moving things around and, we're dealing with relatively anemic CPUs and we don't want to waste a lot of processing time. The VDP can tell us if 2 sprites are overlapping in some way, Okay. Now it goes into tell us here. It'll tell you that 2 of them are, but they won't necessarily tell you which 2 are overlapping. It's better than nothing, but it helps. You're going to have to then figure it out on your own if you care. And we ultimately will care because we'll have a sprite that represents a ball that might be moving around on the screen. And when the ball hits the paddle, we'd like to know whether the visual aspect of the sprite is in contact with our paddle. It's easy to figure out if 2 rectangles that represent a bounding box, say, around a sprite, and remember I said this is a 16 by 16, so it turns out there is this idea of this bounding rectangle around here, but visually it looks like this. If I had 2 sprites and one was a round ball and one of them was this paddle, and they came together like this, the corners of these 2 rectangular sprite regions will collide before the visual pixels start to overlap. Okay? So that's what this sort of thing is supposed to be able to help us with. All right? Now, hopefully, it doesn't say exactly that that's how it really works. I certainly hope that it does it on a visual basis as opposed to the bounding rectangle basis. It'll make it helpful to us, because you don't want to have a game where a ball comes down and then bounces off your paddle. Visually, it hits and goes back up before you can actually see it touch, That would be a bit of a drag. If that is the case, we'll just have to be careful about how we design our sprites and make sure that they look okay, even if we can't detect them the way we want. Now it talks about the sprite pattern table here, and we already saw this before. Which register, where is it, how big is it, and stuff like that. And it also then goes on to talk about, if you got a sprite that's a big one, obviously you need to put more bytes worth of data in there to describe a 16 by 16 than you do if it's an 8 by 8. For now, we're going to stick with the 8 by 8. Keep it simple. Just get the thing to go. There's enough problems we got to worry about. Let's not get too cute right now. So, in addition to the sprite pattern table, there's an attribute table. The attribute table tells us where the sprite is supposed to appear on the screen. Those are the first 2 things that are in this sprite table. And then the second 2 bytes in the sprite attribute have to do with what the color is supposed to be. And the N here, remember, TI wanted to call these names. All right, that's the tile number. Just like when we put a lot of visual elements on our screen. Let me move the joystick here. You'll see in a minute why this lights up and stuff when I move the joystick around. Each one of those little arrowheads is sitting in a cell on our display in graphics mode 1, and each one of those arrowheads is, you could think of it maybe as a character if this was a text screen, right? And each one of those characters has what they call a name. I like to call it like a tile number. That name is the index number into the name table, where it goes to get the graphic image of that tile that I explained before when we were just playing around with regular static backgrounds in the last video that I posted. So this here is the number 0 to 256 that represents what image do I want to put on the screen to represent in this location the sprite, and this will tell me what color it's supposed to be. Okay, so here's their demonstration that says sprite 0 will always appear in front of number 1 and will always appear in front of number 2 and so on down to 31, and behind number 31 is where the regular graphics tiles would normally go. Then they have a nice zoom in here on what all the bits are of those 4 bytes. The first byte is vertical position. 0 is on the top of the screen. So if we go back to here, if I told this sprite to move itself up to the vertical position of 0, it'll go up to the top of the display area. Horizontal position 0 is on the far left. So if I move this sprite up like this, it's up in the upper left. It's near, this is 0, 0 up there. So the position can be anywhere from 0 to 256 in the horizontal. Now, if you move it over to 256, the astute viewer might notice it becomes invisible. And that's exactly what would happen. If I move the position all the way over to here, it goes off the screen. Okay? Now, they also provide a way for it to go over here on the left. The idea is kind of move it to a negative position if you want to. But how do you do that when you only got an 8-bit byte and all of 0 to 256 are already meaningful? There are no other values you could put in that byte to say, put it so far over to the left that you can just see, maybe just peek a little bit to the right, okay? That's what this early clock thing is. If you set this bit, you can move it off the screen to the further to the left, as it says here, off to the left of the screen. I'm not going to deal with that today. I'll leave that as a test to the viewer. When we get into more of a fancy game, we'll play around with that later. But that's what this thing is for, if you're wondering. This is the color of the pixels that are on in the sprite, and the off ones become transparent. This then implies that we can only have one color for all of the pixels that are described by a sprite. The name bits are obviously which one of the patterns you want to use for the sprite in the sprite pattern table. And then vertical position is the only one that we haven't talked about yet. And since there's fewer pixels in the vertical position than there are in the horizontal position, if we dig around in here somewhere, here we go, it'll talk about how you can make it flow off the bottom of the screen, because you can obviously give it a vertical position that's greater than the last, row of pixels. And you have this problem, again, where if you really wanted to go up above the screen, so it just kind of peaks down, you see the bottom part of the sprite, they'll let you do that because they allow you to move the vertical position all the way up to -32 if you want to. So the way this really works is you can put a signed value in the vertical position. And if you think about it, it's kind of screwy because there's more than 128 vertical rows of pixels on this screen. And 127 plus 1, if you have an 8-bit binary number that's signed, equals -128. When in fact, the 128th row is like down here, 2/3 of the way down the screen. So this is kind of a weird thing, all right? Just deal with it. All byte values in the vertical position, think of as an unsigned integer, but the highest possible integer values, the last 32, cannot be used. They're useless, simply because they're off the screen. And they recycle those last 32 possible values, and they treat them, and only those, as signed values, so you can get this -1 to -32. All right, so you have the ability now to move a sprite so high it can go off the screen vertically, so far to the left it can go off the screen to the left, so far to the right it can go off, so far to the bottom, down here it can go off. And it can peek in then from each one of these 4 sides of the screen. Here's a section where they talk about the same thing with the horizontal. If you make it really big, it goes over here. And the 0 is on the left. You want it to go further, you use that early clock bit if you want to do that. And they point out the fact that the name of the sprite is the number of the sprite to get the picture out of the sprite pattern table. Now they give you a couple of examples down here as, an 8x8 and a 16x16. Different size sprites. I'm going to use an 8x8, okay? And they talk about the early clocks and the color and all that. All right, so that's the overview. What differences do we make in our code? We're adding this sprite attribute table. We're putting data in here. And we're adding the sprite pattern table. That's all we're doing. In contrast to the M1T1.asm example program where we just did the graphics 1 mode without the sprites, okay? So what did I do? I copied some of the star and the ball data. Actually, the star came from the example sprite diagonal. In here, they talk about making sprite patterns, and there's a star in here or something. I just copied their value. There's a smiley face, and here's a star-ish looking thing, and so on, okay? So that's where I got that one from. I think I designed this one myself. I just guessed at some pixels. And now I have the horizontal paddle. And we talked about these patterns before. And remember, the first byte is the top 8 pixels, the second row of 8 pixels, and so on as we move down in our 8x8 grid of pixels. So the top half of this tile is zeros. It's off. In other words, it's transparent, right? That's why this thing doesn't have a square shape. It's just this slab here. I then have 3 rows of pixels that are on, and then I have 1 more row that are off. So this here is, as we'll see, a magnified 8x8 sprite that is described using this entry right here, okay? So we could say it has 3 rows of pixels on vertically and 8 on horizontally. But, as we'll see, the magnification's turned on, so that's all doubled. And we'll really have 6 pixels vertically and 16 horizontally, all right? And a whole bunch of transparency above and below it, okay? Yeah, I replaced some of the patterns we played with last time with these arrowheads, and you've already seen them when I move around the joystick. Now, remember, there's a name table down here, which tells us what the tile numbers are, what pattern do I want to put in the, statically on the screen in each one of 768 total positions on the screen. Now, I could have done this $- name table, which I used to define the sizes of the other tables, and that is the size of the table. However, some of that table is not actually used, so I just hard-coded an equate over here to set it to 768. Because that's how many are actually used. And I don't want to have this. You'll see I use this in as kind of like an LDIR command, the instruction that I use to copy all the data around. I don't want to copy any more than I have to because everything takes forever on a slow CPU like this. So I wanted to make sure that even though the table was big, I'm using this symbol to represent how many bytes there are in that table so that if and when I want to move it around or copy it, or in this case, I'm going to pad it to values, I only do as many as I have to. Initially, before I do anything, I set them all to 0, okay? That means that the tile number, the pattern number is 0, and up here, as you can see in the pattern table, I made the 0th pattern all blank. It's just set to the background color. All right. Now, if we go down and look at our color table, I got a whole bunch of rando colors in here. And what do I got? A 21 for the first 8 patterns. Okay. So what's that? A 2 and a 1. You got to go back and look up what the pattern table was. I can't remember. A 1, I think, is black. That's why it's black. One of those is black. All right. And the 2 is a medium green, and that makes perfect sense, because when I actually put something in there, they're all green, right? That's medium green over black. So these here are going to be what? Green on black? Actually, that's these. These are going to be, what did I make those? Light green on? Maybe that's why the color looks weird. Hang on a minute. Did I miss? I might have just left junk in this table. Yeah, that explains why some of them look a little different than others. I got green on black, and then I got a light green on black. So when you do this, some of these look a little bit lighter colored than other ones. So that might explain that. Whoopsie. Why don't we fix that while we're in the neighborhood? In fact, why don't we just set all these to 21s so I don't have this problem. It's supposed to be 32 entries in here. Let's go ahead and compile that up and run this new one. See if that changes the way this thing looks in any real way. All right, so I redid my SD card, boot it up, fire it up, and run it. Here we go. Let's see what it looks like when I move it around now. Is it more consistent? No, I don't know. I mean, NTSC video is always a little bit awkward, It's fine. But it's consistent, okay? All right, we're better than we were 10 minutes ago. So these then are the colors of all the patterns that can show up on the regular old name table. And these have nothing to do with the sprites. Those are just the the main grid of patterns, the main tiles on there, okay? So what do we've got here? Okay, so let's look at our sprite. We have a vertical position, we have the horizontal position, the pattern name number. I'm using pattern number 2. And the early clock and color is set to 08. If we look back then at the table here, right, we got the vertical, the horizontal, the name. The early clock, the 8 is down here, so I'm on color number 8. And color number 8 is supposed to be medium red, okay? That's not exactly medium red, but I don't, it could be my capture device not being quite right. It could be, part of the analog circuitry not being right. Maybe my crystal's off a little bit. I'm not entirely sure. It's red-ish. Good enough for now. While it's mildly annoying that we don't have a beautiful color, we are living in 1981 and 82 here. That's the kind of stuff that we have to tolerate. Okay, so this is the information about the sprite. So let's look and see what's this all about, right? Well, remember the vertical position. We have 24 rows by 32 columns. So when this thing first booted up, you'll notice that my paddle was in the middle of the screen. Well, where's the middle of the screen? Well, if I'm 24, and each one of them is 8 pixels wide, that's the total number of pixels across the screen. Divided by 2, that's the exact center pixel on this screen. Now, because I'm magnifying my sprite to 16 pixels wide, I want that thing to be backed off, because the position of a sprite is not where the middle of it is, it's where this upper left corner is. Okay, and in this case, remember, it's actually part of this transparent area as part of the sprite. So the upper left corner of my sprite is really up here, okay? So what I need to be able to do, I don't want to put the upper left corner of the sprite in the middle. I need to put the upper left corner up and to the left a little bit so that the image of the sprite's in the middle of the screen, right? So I got to subtract half the width of or rather half the height of the sprite here. And the same thing in the horizontal position. I got 32 total wide. Each one is 8. Half of that's the middle horizontally. And the same game to get the center that direction. Okay, I think I misspoke earlier. This is the calculation for the vertical. This one's for the horizontal, okay? So we're in business. We can put whatever pattern we want out of the 256 possibilities for our sprites, wherever we want to put it, by simply storing the X and Y locations of where we want it to go and what we want it to look like in this table here. All right. Now, this is part of the data that I send down into the VDP dynamic RAM when I boot up. So the code up here should look familiar when we start it up. We otter a bunch of register values down there to set it up, which we talked about last time. Then we just sent down all the VDP dynamic RAM stuff, and we got to do it slowly. I talked about the timing last time. We'll look more closely at that again in a few minutes, so that we know we can get it to go down there, even if the screen is being painted. Okay, if we do this after we set up these registers, no matter what the VDP used to be doing, it's going to be painting the screen by the time we get down here. So we need to make sure we don't do this too fast. We'll just assume that when we're sending all this data down there, either some or all of it could be moved while the VDP is drawing in the active part of the display. Okay? So we just err on the side of safety. Once that's all done, we fall into a big loop down here where we're going to calculate basically where do we want the sprite to be now based on reading the joystick. I'll talk about this logic in a minute. It took me a few minutes to get that right in my head. When I'm totally done with that, I have the X and Y coordinate information in the DE register, as we'll see. And I store that into memory in this address where that label is paddle 0. And we just saw what that was a minute ago. This sends two 8-byte values, the 16-bit value of the DE pair, into the vertical and horizontal position bytes in that sprite attribute table. Okay? And it does so. Remember, this is in the Z80 memory, not in the VDP right now. Once that's been stored in down here, and I overwrite what was there before, okay, I'm down at the bottom of the file here, I'm updating these 2 bytes right here, which has the label paddle 0 you just saw, okay? That's what that load instruction does there. Here's where we were looking, okay? We'll go back and look at the rest in a minute. Big picture first. When I'm done with that, what do? I want to fill the name table with all 768 characters. What I'm doing is I'm going to store this B register in, and I'm going to play my LDR game where I just set every value in the array of bytes, starting at name table, going up to 756. Actually, this is too many. I made a boo-boo. That should be -1. I wrote one too many. It turns out that's actually okay because the data after the 768 are actually not used, but that's not right. We should be more careful. Anyway, so what I'm going to do is I'm going to fill up the entire name table with all the same values that come from the B register. And part of the code I skipped above sets B equal to the name, the tile numbers for the up arrow, the left arrow, and so on. That's part of what we do above to figure out what we want to put on the background of the screen. Okay? Once all that's done, I call this VDP wait function. We'll look at it in a minute. This waits for that interrupt signal to go on to let us know that the VDP finished drawing the active display region and that we now have up to 4,300 microseconds that we can do with what we want before it starts drawing again. And we saw that table last time, which came from this manual over here. This is the other one of the 2 manuals on the GitHub site for my project, right? This is the 1982 manual. And in here, this is this timing table. I showed you this before. So what happens is, for 4,300 microseconds after the vertical interrupt signal, I can write continuously as long as I don't write more often than once every 2 microseconds. As I mentioned last time, if we're drawing in the active display area at the point in time when we're moving data, I cannot go more quickly than 1 byte every 8 microseconds. So that's why this is all important, that we keep track of when we can talk fast, when we can talk slow, and all this other stuff. So what we got here is we wait until we know we're in that vertical blanking region at the bottom of the displayable area, at which point in time I say go from this address for that many bytes into the VDP memory at this address here, because that's the address where the Sprite attribute table is. And this allows me to replace all the Sprite attribute data, kind of like when no one's looking, right? And we'll see that this VDP write function here goes faster than the VDP write slow function did that we called earlier on when we were initializing everything, okay? When we're done with the Sprite attributes, we want to update all the name table. We'll do the exact same thing, and this time we'll write it in at 1,400. These numbers are the addresses that we used when we configured our VDP. I went down to the bottom of the file here. Remember, these are the registers. I talked about this last time. We'll talk about this one here because I changed it for this version of the code. But this is the initial values of the registers 0, 1, 2, 3, 4, 5, 6, and 7. All right, the default background color and all that other fun stuff for the border and whatnot. Short of it is this tells us the addresses of where all these tables are. And this is the same settings we used before. My comment is wrong. Boy, I'm a bad boy. Bad Johnny. Both of these are wrong, actually. I don't know what this one is. I should just delete it. But this is 8 by 8 with magnification turned on. And we'll look at that right now to verify that that's true. I'm writing in a register 1. I explained how this works last time. And I'm setting in a value that's E1. So let's look and see whether I've got my wits about me here. So let's look at register 1 here. E1, well, the least significant bit means turn on the magnification. This is your size bit. So if this size bit is 1, we're on a 16 by 16. If it's 0, we're on an 8 by 8. If this is on, it doubles the pixels horizontally and vertically. It makes it more blocky looking. But that's fine for the demo that I want to do right now. It's also, what is it, E1? So that's a 1, 1, 1, 0, 0, 0, 0, 1. That's perfect. We have the interrupt enable flag turned on here, so we can look at the interrupt pin coming out of the VDP. I can put my scope on there. I mentioned that last time. We're going to look more closely at what this thing's doing on my scope in a minute and see that all our timing's okay. So that's why I had to have this thing turned on. Okay? So what do we got? E1. This one was a C1. I got a C0. So that thing was 8 by 8, no magnification. A C1 is an 8 by 8 with magnification on. I'm going to just fix my comments while we're here. Okay, now this is correct. I'll push this up right when I'm done recording here. Okay. So this is the only thing I changed since the previous video. Is probably the the setting of the interrupt bit and turning on magnification. In fact, this is probably the version from the code in the previous video right there. Okay, so that's the mode I'm in. The table locations are the same as they used to before, and we're just filling in 2 more tables than we did from before. We're setting up the Sprite stuff, okay? So here's the code we were just looking at. We're going to wait. When we're done waiting, I'm going to try and hurry up and update only the data in the Sprite attribute table and that name table for only as many bytes as I have to, because if I write the whole thing, it could take a long time and I might not be able to finish it before my 4,300 microseconds passes. I can go fast, but I can't go forever, okay? So I want to minimize what I want to send. I don't want to send it as fast as I possibly can without getting too fast to mess up the VDP. So this is the bottom of my main Sprite loop, which is our main game loop here, all right? So that leaves us with, what do we do in the loop, right? So here's me, initialize it. We fall into this loop. I'm going to leave some of the details as a task for the reader here and give you a kind of a high-level view and then start looking at the timing, because that's kind of really the main concern I have on this video today. So what are we doing here? I'm going to use the V register to remember the value of whether I'm going up, down, left, and right. So what we'll see down here is 4 separate chunks of code that are almost entirely identical. We'll look at one, and you can figure the rest out based on that, okay? Which is literally right here. This is like the whole thing. Set it up and then do this 4 times. Once for the up, down, left, and right directions, okay? What happens by the time we're done is the B register will have a number in it that'll go from 0 to basically 16, some of which values are not possible, okay? And we're going to use the B register value, that 0 through 16, to figure out what tile number we want to put in the background of our screen. So when I'm not moving the joystick right now, you'll notice it's blank. And this logic down here, when I'm pushing it up, you can see I load B into A, I OR in a bit, and I put it back in B. And what I'm doing is I'm setting that bit to represent the fact that I saw the switch inside the joystick for the up direction, all right? So that bit will be on. If that's the only thing I'm doing, by the time I get to the bottom of the loop, B will equal 4. If I'm hitting up and right at the same time, then the value will be 6, and so on, all right? So these are just going to all be ORed together as we go through this code. Yeah, I could have optimized it if I thought ahead and designed the hardware in such a way that all 4 joystick bits were in the least significant 4 bit positions. I don't know. Sorry, sue me. You get what you pay for. I wish I would have done that. I really did. I'm like, oh, it would have made this code easier. I could have just read it and been done with it. I still can, in theory, YouTube comments below. That would just require me to define more names or rather patterns, I should say, in the pattern table. Okay, or move the ones there around and so on. Yes, I could do that and get rid of some of this excess code and speed it up. When we get to super optimizations, we'll try that. Okay, so what's the point? B is going to get filled in with a number that I'm going to ultimately use to represent the name, the tile number, for each and every one of the positions in the background here, right? So that's why they turn on when I'm moving the joystick around, and why they all go off, because B is left to set to 0, and 0 is a space, I like to say, as you saw a minute ago in the pattern table. I load DE with the 2-byte value stored at paddle 0 that we just looked at a minute ago. That represents the X and Y position, the horizontal and vertical positions that are in the Sprite attribute table. And remember, this is a little endian machine, so E is the first byte in that table of bytes, and D is the second byte from that table, all right? I read the joystick in the accumulator. I then put that in the C register because I got to mess around with the accumulator a lot here. And I don't want to keep rereading the joystick value. And this is not a performance thing. This is a metastability thing. I work with high school kids in my FRC robotics club, and this is something that a lot of people don't quite get on the first try, and it's tricky. I make the mistake too. In fact, I think my first draft of this code, I kept rereading the joystick. You don't want to do that. You want to read it once and only once, and then do all these decisions down here based on that one reading that you took one at that single point in time. For example, one reason you don't want to read it repeatedly while you're ORing these bits together to decide what character you ultimately want to put in the background is if I read it and then I read it a second time. The first time I read it, I could see the joystick suggesting that I want to move up. If I move the handle really fast, the next read could suggest I want to move down at the same time. Which is not even possible. So if you're building a video game, don't be a dingus. You can keep your code much simpler if you read it once and only once. And that way you can't get up and down on at the same time. You don't have to resolve these weird situations. You might want to do it anyway in case there's some other bugs going on, but no, you really want to do this in an atomic sort of way. Doing this on a robotic device with things moving around, you got ballistics and gravity and momentum and all this. No, is the lever hitting this limit switch or not? And as you go through logic, it's just like this, where you've got many things you're checking based on this one reading. You can end up with it's open and it's closed, or I'm going up and down at the same time, which is really annoying. You definitely do not want to debug that, okay? And I don't even check for it in my code here, by the way. Again, I probably should, but I don't. Okay, what else am I doing? Yeah, so I sort in the C register so I can batter around A and keep C around and reuse it over and over and over. How do I do? I say, hey, I end it with joy up. Up above in the code, there's an equate that sets this thing equal to whatever bit position is set when the joystick is in the up position. If that bit is on, I fall through here and process, do what I'm going to do if I think the joystick is in the upward position. If it's not in the upward position, I go down here to I'm not going up. All right. Now remember, 0 and non-zero, this is inverse logic, right? There's a pull-up resistor, remember, on the input buffer that we use to read the joystick. So I'm plugged into J4, right? So here's my up, down, left, right, and this is pulling up. If I'm not touching the joystick, or it's not even plugged in at all, All these are ones. If I move the joystick into the up or down or whatever direction, what the joystick is doing is it's connecting whatever pin, whatever signal, to this ground pin over here. Okay? So when it's 0, it means that that direction is activated, and if it's non-zero, it is not activated. So that's why this is doing this. So if I do have the stick in the up position, what do? I load A with B, I or in the forward, and I just explained that to death up here, and I put that back in B. So I'm done with that. Then what do? This gets a little bit more interesting. I wrote this code a couple of different times, and I ended up with this because I wanted to be able to parameterize the rate at which the joystick or the paddle moves around on my screen. And I wanted to be able to do it in such a way that the code doesn't have to be completely disrupted and hacked every time I want to change the speed. So I have a nice little equate above at the top of the file. It says in the vertical motion, how many pixels do I move the paddle each time I move it? So in the horizontal, notice that it moves faster than it does in the vertical dimension. Okay, the vertical direction right now is set to move 1 pixel every time I go around this loop. So you can actually see how long it takes to go around this loop. Now it's artificially slowed down by the fact that there's that wait in there. Remember, I'm waiting for the screen to be updated every time I go around this loop. So what this is doing right now is it's moving from the top down or the bottom up 60 times a second. That's 60 pixels per second. In the horizontal, I set the speed to a faster number. Honestly, I can't remember what I have it set to. I don't know if it's set it to 2 or 3. Let's go back to the top of the file and have a look-see. Those are all defined up here. Yes, I move it at 3 pixels every time I move it. All right? So let's go back to the code we were just looking at, which is right here, or not. Which is right here, okay? So let's see how this works. I load A with E, because E is my Y position. Up and down, I'm changing the Y position, okay? Now I'm going to work ahead here in order to simplify my code, so I don't have to have a bunch of jumps and things in here. So I got a job to do here. If I'm moving it up and it's already at the top of the screen, it'd be nice if it stopped, right? If I'm moving it to the left, I don't want it to, go off the ends of the screen and stuff like that, all right? So I got these limits. I have to clamp it on those limits. So how do I do this? I get the current value, put it in the accumulator. And then I just assume that I'm already at the minimum value. Remember, the top row is 0. So when I say minimum, I mean that number. Make sure that E never becomes less than min. Okay? So what I do is I say copy E into A, copy the current position into A that we stole out of the memory up here, right? Put it in the accumulator, just assume that I'm in the upward motion, that the joystick wants me to move up and I'm already up there, or I'm 1 pixel away and it's as far as I can ever go and never go any further. I'm going to just stick that into E right here. That's what I'm doing. Then I'm going to ask, is the accumulator, how does it, is the accumulator, what I want to know is it less than the far as it can go in the vertical direction, which this is set to 0 right now, plus whatever the speed setting is set to. So this is actually 1. I'm saying, tell me the difference between the current value in the accumulator and 1. Logically, is it so close to the minimum value that if I subtract the speed value, am I going to go too far? That's what this thing asks. And if the answer is yes, it turns out the compare instruction does a subtract. What this really does is it says accumulator minus this, which is 1. Okay? And now down here I say, is there a carry? The carry will be set if we did a borrow during this subtraction. This carry and borrow is really the same flag. When you're adding, it's a carry. When you're subtracting it, we call that a borrow. Carry goes the other way. Okay? So, if we got a carry, we know we're already at the limit, or we're so close to the limit that if we do this subtraction, we will either be at the limit or go too far. So we don't want to do that, and we just skip over it down here. Okay? Now, if we're not so close to the limit that we're going to end up too far, then by all means, adjust it based on however far we're supposed to go every time we make a leap, and put that back into the E register. All right, so that's what this does. And the other four directions all do the same thing. The B value gets ORed in with a different value, obviously, from the dock above. If it's going down, it's a different bit, and so on. This logic here is very similar, except for we're using the max instead of the min, we're subtracting instead of adding, and we're dealing with no carry versus carry. You know, when you're adding and subtracting, you got to reverse these things, all right? So there's your up, down, your left, and your right. All of them have a different bit to represent whether the direction is being, whether the joystick is trying to move it or not. And we do different math here, ever so slightly different math, whether we're going up and down or left and right, okay? As you can see, when I'm going left, we're got an adding. And when we're going right, we're subtracting when we do the comparison logic, okay? I'll leave it to the viewer to work this out. I don't think I'm in a mistake simply because it works, but I could be wrong. There's comments below. I always welcome pull requests and things like that. And then we get back down to the bottom of the loop. That's the whole program right there. Let's watch this thing go. Let's look at some of the timings and do some tweaking here, okay? Now, in order to make it easy to monitor this with the oscilloscope, I got a couple of notes in here, okay? I just point out, if you're not going to really move anything on the screen, it's just sitting here. Why go through all this work to update the name table, update the sprite table, blah, blah, blah? Why am I moving around all this data every time through this loop if I don't have to? Okay? Well, that'd be nice, but it'll make it harder to check to see what's going on the oscilloscope, because I can clip it on there right now while I'm doing nothing at all, and I'm seeing the pattern go on my screen. This is why, okay? And, oh, by the way, this game, as it were, does depend on this call down here to VDP wait in order to pace the game. If I don't wait here, all right, and I start moving the joystick, what'll happen is the first time that goes through that loop, it'll go quicker than all the other times. And what'll happen is the game will be all jerky and jump around. And normally in a game, even if you're doing nothing, something else is going on, like time is burning up, or something is moving by, or you're moving the background around and stuff like that. You usually need something to pace out your game. So right now, brain dead simple, no matter whether we're moving or not moving, everything is done every time we go around this loop. That way, we build all of our data, we do all this stuff. It might take a variable amount of time. As long as we get it done in less than a 60th of a second, this will waste the rest of the time for the 60th of a second that we have to wait in order to start doing the actual transfer into the VDP RAM during the vertical blanking interval, okay? Now, let's look at some of these subroutines. How do we wait? What are we doing in here? Well, I go into a spin loop. I read in the VDP register. That's the status register. I should probably put a comment in here. I don't know. Be nice. Read the VDP status register. Okay. Let's have a look-see at what's in there. That's actually documented right after, like, register 7 down here, isn't it? Nope, that's 1. Which is right down here. Okay, there we go. The frame flag is what we're going to be looking at. Here's that 5th sprite indicator that there's too many per line. Okay, here's the collision that we talked about a minute ago, or the coincidence they like to call it here. And this is the 5th one if you got too many per line. All right. So what I want to do is go into a spin loop and wait for this thing to turn on, because like it says down here, when it gets to the bottom, that goes on right as it finishes the active scan area to let me know exactly when I can waste that time doing a high-speed copy. Otherwise, I got to do a low-speed copy. Okay. So that's what I'm doing here. I do this. I'll check the high bit. I probably should have used a symbol for that, but I was lazy. Maybe I'll comment it. At least I'll give you that much, all right? Frame flag on. Okay, if it's not on, I just spin to crazy on this thing, all right? Waiting for that to happen. As soon as it's on, I return. And we go back up to here. And I know that it's okay for me to do this, provided I don't do it too long. So what am I doing? I'm calling VDP write, VDP write. Two different chunks of memory I'm writing out, okay? So what does VDP write do? Okay, comments up here. Copy the buffer to VDP. Okay, we saw this before with the slow one in the last code. But this one's a little trickier. I need to make sure that it runs just the right speed. And I put in here a note. It requires at least 2 microseconds per VRAM write during that time after it generates the field flag we just talked about. The rest of the time, I got to wait 8 microseconds between writes, at least. DE is the target in the VDP DRAM. HL is the source address in the Z80 address. Memory address range, and BC is how many to write, and so on. So let's see how I did this. And we're going to see I got a couple of different versions down here. And we'll look to see what's going on. This one's too fast, one's too slow, one's just about right, okay? So all of them start the same way. Get myself set up. I write down into the VDP the VRAM address that I want to be transferring my data into. We've seen this before. You put the, the least significant byte, then the most significant byte, and when I do that, I have to set this bit to let them know, and I'm really trying to configure out, getting ready to do a write transfer into the VDP. I laughingly noticed I was doing a push BC pop DE in my last video, and I'm like, why am I wasting all that time? This does not need to be slowed down. Why don't we do it in a sane manner? So that's an upgrade since before. I put into the C register the address of the VDP RAM port that I'm going to use to output all the data into. And we talked about this last time before. Now it gets interesting. Exactly how do I want to send that data? C is the IO port address, so I can use things like otter or out I, okay? And I can do different variations of this whole thing. If I just go into an otter and let this thing do a full speed, what I end up doing is what? First of all, Otter can only do up to 256 bytes. And if I need to move more than that, I got to be careful, because remember, BC is my byte count. I copy it into the DE register, because if I'm going to use an Otter or an out I need to use the C register for this instruction to work. And all these instructions will destroy the B register as collateral damage when they execute. So while I do pass in the length in BC, I need to move it somewhere else to use it while I'm going. So what's going on in here? I'm going to put it in B. I'm going to put this in A. I'm going to figure out whether or not the length ends in a double zero. In other words, there's an exact multiple of 256. If it is, and I OR the accumulator with itself, I end up with a value that is equal to 0. And if it is equal to 0, I'm going to just do this loop in what I would argue is the obvious way. And that is send as many bytes out as there are in the B register to the port in the C register. That's what this instruction does. It leaves the B register set to 0 when it's done. And then I'm going to do this repeatedly, because remember, the D register, because it's a 16-bit pair at the DE register, right, is representing how many 256 byte blocks I really want to move when I do this right loop logic here. So let's do the simple case. Let's say I want to send exactly 100 bytes in hex. That's 256. DE at the time I get to the code right here will be exactly equal to hex 100. This will set B to 0. This will set A to 0. A is still 0. We come down to the loop. We do an otter. The length is 0. When you do an otter with a length of 0, it moves exactly 256 bytes. I come down here and I do a decrement D. What's in D right now? 1 was in D. I decrement it. It becomes 0. This is false. I return. I'm done. That's exactly what I want. Let's say I want to move 101 in hex bytes. Now it gets more interesting. Okay, I put the E into the B register. That's a 1. And then I ask, is it 0? No, it's not. I fall down here, and now I increment the D register. So what I'm really doing, by the time I get down right here, I change the 101 that I said I had in DE in this scenario to a 201 in hex, by letting myself do this before I go in this loop. First time I do an otter, remember I needed a 101. 101 was in DE. The 1 is in the B. The otter runs right now and it moves 1 byte. Falls down here. Because I incremented it, D now has 2 in it. It decrements it to 1. 1 is not 0, so it goes up and does this again. Otter left B set to 0 at the end of the first time I ran it. It now does another 100 in hex, the 256. Comes down here. D was a 1. Now it becomes a 0, and I fall out, and I come out down here, and I got the right amount. Okay? If that's not enough for you, work it out on paper. Think about it for a few minutes. It'll make sense. Bottom line is, if you're moving an exact integral of 256 bytes, you got to do something different with this logic than you do if you're not moving an exact multiple of 256. And what you need to do different is adjust this thing in order for that loop to work. Okay? Here's another version. This one uses out I. Now, the reason we have these two different versions is out IR will run at full speed, and the Z80 does this round and round and round on its 10 megahertz clock. It does exactly 2 microseconds per transfer. Actually, if you look up the timing in the manual, it says it takes 21 T-states each time it goes around the loop when B is not equal to 0. This is the outer instruction right here. So actually, it takes more than 2 microseconds, ever so slightly. It takes 2.1. At 10 megahertz. But, as we'll see, this won't work. Even though we're within the speed limits that these guys claim we need to be. Which means somebody's lying. I suspect what happens is that the crystals on the Z80 in the VDP are not perfect. Nothing's perfect. Maybe the Z80 is going slightly too fast. Maybe my VDP is going slightly too slow. Blah, blah, blah. I'll show you what happens if you do this. And you exceed that speed, it screws up. Okay? So what I needed to do is come up with a way that runs slightly slower, and this is what I came up with. I can do this in about 3 microseconds per loop. Using this slightly different logic here, okay? Remember, out I is just like out IR, except it does not iterate. It does one and only one transfer, but it still decrements the B register because it counts. Probably uses the same transistors and stuff inside the Z80 as the other instruction, but it just simply exits early. It doesn't iterate. It just does one iteration and stops, okay? So it's going to do the same thing. It's going to write into the C register, write out the port in the C register, which sends it over to the VDP. And it's going to write data from memory that's in the HL register, which is up here. All right. And before we even come in here, the HL is supposed to point to the source address, right? So that's just a given. That's how the instruction works. And when we fall down here, we have to do the counting. I had to do the counting myself rather than let the instruction up here do some of it. And because even this one doesn't do up to, 64K in one fell swoop, it's doing it in chunks. You got to do the screwy logic down here. I got the same screwy logic up here. Okay? I'm asking, is it an even multiple or not? Why I use a very different style, I do not know. But it's fine. It's doing the same thing. If I increment and decrement D, this will set the 0 flag. If E equals 0, I probably should have made this consistent above. I like to keep my readers and viewers on their toes, I guess. That's my story, and I'm sticking to it. Anyway, if E is 0, we play the same game with the incrementing the most significant byte of the counter. Now, this works a little bit differently. Let's go to this bottom one first here, because this is the easy. This one makes more sense than this up here. Let's go to the one that's just really unnecessarily slow, all right? This was my second choice. I probably should have put the code in another order. This one's easier. We just do one and count the DE register and just throw the B register value away. We don't even care about it. We don't really care about it up here either. But we have to count up to the value in the DE, or subtract 1 from DE each time, waiting for D and E both to become 0. If they're not 0, we go back and do another byte. This is very simple, straightforward logic. What's going on up here? Well, it turns out that decrementing the E register and jumping if E is not 0 back up to our loop takes less time than decrementing the DE register and then figuring out if D and E are both 0 and then going up to our loop. By quite a significant difference. All right? So, this is terrible. This is 4.2 microseconds per loop iteration. The one up here is 2.1. On the scope, it looked like 2, okay? And the one in the middle is going to come out to 3, as we'll see on the scope, all right? Pretty straightforward, okay? So do only one E register and wait for E to become 0, and then decrement D, and then go back to decrementing E again. This is the same overall logic as we did up here. But Otter decrements the least significant byte of the counter as part of this instruction. And it does it too fast for our needs, all right? So this is really the same thing as that Otter loop. It's just that I'm doing the least significant byte decrementing here to waste a little bit of time, all right? So this is the one that you've been seeing me play around with on the screen in the beginning of this video here, all right? All right, so I'm going to clip some scope probes on my 9918. I got the big breakout header on there, and I got the yellow probe on the interrupt output pin, and we'll see that goes true. It goes low, because it's got a bar over it, once every, 60th of a second. And then I can look at either the reading or the writing signal. Now, you think about what's going on in this code here. This is always writing when it's spinning through here. All three of these all do the same thing. Out IR or out I in a loop. These are writing continuously when they're running. So what happens is if I clip a scope probe on here and I look at this write signal, I should see it going a whole bunch of times up and down, and then it'll go idle again while it waits for the next 60th of a second. And then when that happens, it'll go in a burst and send a bunch more data and then pause in a pattern like that, okay? In fact, I should see the interrupt signal go active, followed by a big old burst of writes, followed by a pause while we go around all the code up here, right? Oops, too far. When it does all this top stuff in my loop, it's going to reread the joystick, do all this other fun stuff. Then it's going to play all these games, copying things, setting up the background image and things like that. Okay, in our buffer where we hold all that VDP initialization data. Then it's going to get down to the wait right here, okay? When the wait is running, I'm spinning, doing an input operation. I should then see this signal going on and off and on and off and on and off like crazy. And that should happen and continue to happen until the next time I see this interrupt. The first time I see that interrupt when I'm reading, that's when this thing returns, and then I go and do this. That's when my burst of writing starts again. And I see that happening over here. Now, I only have a dual trace scope. My logic analyzer's broken. Boo-hoo. So I need to maintain the reference on the interrupt pin in order to trigger my scope. And I'll do a trace while we watch the read, and I'll do another trace when we do the write, and we can kind of merge the signals together in our head and see what's going on and figure out where all the time goes, all right? So let's start with this picture right here. This is triggered on this blue marker here on the yellow trace. It's very small. There's a tiny little spike here on the interrupt output, and this is the writing operation that takes place right after that interrupt. Now, this is what I call the Goldilocks code, which, if we look at my doc, is the one that we have commented in right here. This is the one that hopefully goes at the right speed, okay? Not too fast, not too slow. And what we're looking at is that it takes 2.7 milliseconds to copy all of the name table and the sprite attribute table into the VDP from the Z80. That's what this is showing us here. This one here, I zoom out a little bit, and you can clearly see here's a write burst with an interrupt that triggered it here, and here's the next write burst over here. And if you could look in, I mean, it's like 1 pixel wide on my oscilloscope that triggers here. This is running at 60 hertz. You got your 16.66666 period modulo the accuracy of my my ability to move these cursors around here. So this is what it looks like when it's running, right? So you get an interrupt, I update what's on the screen. I then, in this amount of time, is where I'm reading the joystick and deciding what the next picture is going to look like and updating my copy of the buffer initialization data that I'm going to write into the VDP over here the next time I have an opportunity to do so. In here somewhere, we should be able to see how long it takes me to do the work based on, if I had a third trace up here, if the reading started here, waiting for the next interrupt signal to go on, I would know, here's how long I took to do the write, here's how long it would take me to do the processing to prepare for the next one, and here's how long I did nothing, waiting for that next interrupt to occur. As long as I'm reading more than 0 time over here, I'm ahead of where I need to be in order to keep the game going at 60 frames a second. And that's our goal. Now, we can take one reading. We know that from the end of one of these memory copy writes to the beginning of the next one is 14 milliseconds out of the 16. I mean, we know how wide that is, that's all. You can also see, if we zoom in really close here, there's a little interrupt trigger right there, okay? So I guess that's the value of this screen here. Now, if I move the probe from the right signal over here, which is the last one was on, and I move it over to the reader here, but I leave the cursors where they are, I can see, even with electrical noise, that's you know, it's one of those times where it's nice to have a noisy circuit. You can actually see here where all the writing takes place because of the glitchy power and stuff like that. Bad grounding, shielding, and massive connector hanging off the board, wire everywhere. Yeah, that's useful. So, you know, I'm not lying. There's the interrupt. It's the trigger. The writing takes place here, and I didn't move the cursors. Here's the reading taking place. So this is the amount of time left over. That is the amount of time it took me to read and figure out what I want to do with the joystick, and then the LDIR to pad all the background name ID numbers in the display area. Then this is me in that VDP wait loop. Well, if we want to know the actual time I spent waiting, it's 12.32 milliseconds, give or take, right? And therefore, the remaining time of the full period, which was 14 minus the 12.3, giving us what, 1 point, whatever, about 1.7, rounding off, for the amount of time it takes me to update the game for the next frame, which is great. Unfortunately, the game is really simplistic, and that actually is a fair amount of time. Although I think a lot of it almost all that is the LDIR that obviously updates that the cached buffer of the name values. So if we write a game that has a lot going on, we got to be careful we don't burn up too much time. We'll have to get creative as the games get more sophisticated. That's all. Here's an actual measurement of the remaining time that we don't yet have, but you can still figure it out. Here's the interrupt to the time I start reading. It's 4.32 milliseconds, which is, of course, the full write time followed by all the calculation time of what I want to put in the next frame. Just for reference, here's a zoom way in while I'm pulling on the reading. And you can see I got the 2.84 microseconds while I'm spinning on that VDP register, so I'm not going too fast there. Oh, this is the write speed. This is me writing to the next write, to the next write, and so on. And there's my 3 microseconds here, okay? Approximately 3 modulo the scope resolution and my ability to set the cursors, all right? So I'm more than 2 here. All right, so that's the Goldilocks code. Well, if I reburn the SD card, reboot it, and fire up the code that runs too fast, that's the Otter version. This one up here, the too fast one, okay? Here's what the timing looks like for that one. Now, these cursors are still set to the amount of time it took me to write the whole transfer to the VDP in the Goldilocks code. So the faster one is obviously faster. That's nice, okay? But, as you can see, if we zoom way in, the period between the 2 writes is basically 2 microseconds. Or maybe it's 2.1. Aha, look. Yeah, I got the little thing off a little bit here. Well, yeah, maybe, whatever. Okay, again, modulo my ability to adjust the knobs on my scope. 2 microseconds, 2.1, give or take, okay? It's going too fast is the problem with that code, even though it says 2 in the doc. I happen to know it ain't gonna fly. Let's have a look-see at this thing. All right, so let's go ahead and turn it on. Turn the other one off. Compile it. Burn the SD card. Put it in the board. Hit reset. Run it again. Find my screen. The initialization works. And you'll see it really does. It's going. But look at that. You see those little angled barber poles? I hope this records that okay on my screen capture. Those are the data bytes getting thrown away. I mean, think about what's happening here. All of those up arrows on the screen right now, all at once need to be turned off. That's all the up arrows on, and when I release the joystick, one of those frames was written with a lot of errors in it. In fact, I would argue all these frames are getting written in full of errors. But because I'm writing the same thing over and over and over again, the errors move around. And eventually all the bytes get updated. It screws up when it goes on, it screws up when it goes off. Although it's not as visible when it goes on. It doesn't, well, that one was. Yeah, all right. So, I mean, look, that's a problem, all right? That's what happens when it goes too fast. You see that on yours. That's what you're doing. You overdid it, all right? Now, obviously, we can run it too slow if we want to. The problem with it going too slow, I'm going to put it back in the Goldilocks here. And I'm going to compile it again. And then run it again. And here we go. And you'll notice now it's not screwing up anymore because we're not going too fast anymore. Okay, so that's the problem with the speed. I'm back in the Goldilocks mode. If you run it in the slow mode, it looks just fine and dandy. However, if you're going slow, you're eventually going to run out of time, okay? So you don't want to waste time. I mean, you can, but if you do that and it takes too long to write it, before you end up into the next frame, you're going to be going too fast during that active display period, and you're going to have other kinds of errors, right? Now, for reference, here is the full duration of the write operation when we're running the slower version of the code, the third one that was in the source code, okay? Now we're up to 3.63 milliseconds in order to finish the entire write operation. And that's in contrast, as you might recall, to the 2.7 milliseconds that we get when we're in the Goldilocks version. And I suspect the Goldilocks version could run a little bit faster, but I couldn't figure out how to write any code that runs more like 2.5 microseconds in order to make that comparison. Maybe we could add a wait state or something, but that would require modifying the hardware. I don't have the room for the gates. Don't want to pay for that. I think we're pretty good with the 3, but it might be nice. So maybe somebody's got some ideas on how to do it better and closer to 2.5 maybe. You know, maybe what I should have done is use an explicit output instruction and count it. I don't know. Somebody want to play around, see how close you can get before it goes too fast and ends up giving you those error pixel values. I'd love to hear it, okay? Well, what do you think? Let me know in the comments below. Thanks for watching. See you next time.